Our first example is the hiring problem. So this is the problem we are facing. We would like to hire one assistant, and we will interview one applicant per day for n days. So if we hire the wrong person, we would have to fire his or her later and hire another one, right? And that would cost us much more than simply interviewing an applicant. And we denote the interviewing cost by C sub I and the hiring cost by C sub H. In this case, what's more important is the total cost, not the runtime. So we would analyze interview and hiring cost instead of running time. Assume that in n days we have hired m people, and the total cost will be given by this, right? This is the cost for one interview, and we're going to go through n interviews in total. So this part is the total interviewing cost. And we have hired m people, and this is the hiring cost. And therefore, this part is the total hiring cost. And our goal is to minimize this total cost. And there's a very simple and naive solution. Let's see how it works. So first of all, we define a candidate 0. That is a dummy candidate. It doesn't exist. All right, it says a least qualified dummy candidate that will set up the baseline. Okay, and we initialize the best person to be candidate 0 and the best quality to be the quality of this candidate 0. And then we begin to interview the real candidates one by one. Okay, so after interviewing the ith candidate, we obtain the ith quality, and the cost of that step is C sub I. All right. And if this quality is better than the best quality, we update the best quality and update the best candidate, and we hire this one. So here we have a cost C sub H. All right. Whenever we encounter a better candidate, we will just hire this one. And if we find another one, we will have to fire the previous one and hire this one again. All right. But the advantage of this naive solution is that it's guaranteed that the final best candidate is indeed the best candidate. But what is the worst case? The worst case is when the candidates come in increasing quality order, right? And then we're going to have to hire every one of them and fire every one of them except the last one. Right? So the total cost is what? Is n times C sub I plus C sub H. And because we know that C sub H is much, much larger than C sub I, therefore we can simplify the form of complexity as big O of n times C sub H. Now, how can we do better? There are usually two directions. One is that we try to solve this worst case in a different way, which is more efficient. And the other one is try to avoid this worst case. Don't let it happen in the first place. By the way, what is the best case? That they come in decreasing order of their qualities, right? So we only have to hire once, hire the first one. But that is just too much to ask. Now let's check out what will happen if the candidates come in random order. The number of interviews is fixed to be n, right? So we concentrate on the number of hires only, and let's denote it to be x, the number of hires, and try to figure out the expected value of this x. So this is the original definition. The big question is, what is this? How are we supposed to know the probability of x being exactly j for every j? We don't know, but here's the trick we can play. Let's define x sub I to be 1 if candidate I is hired, or 0 if candidate I is not hired. then what is the relationship between the value of x and the values of this x sub i's? X is the sum, right? Now we see that x sub I is much simpler than x, right? So it's simpler to check the expectation value of each x sub I because it's either 0 or 1. So by definition, E of x sub I is simply 1 times the probability of candidate I is hired. That is the probability of x sub I being 1, right? And therefore we have that E of x is just E of this sum, which is the sum of the expectation of each variable x sub I. All right? But what is this? Still, we don't know. That's why whenever we analyze randomizations, we have to make some assumptions. Assumptions about equally likely. That is, any of first I candidates is equally likely to be best qualified so far. Without this assumption, we won't be able to continue. So equally likely means everyone has the same chance of being the best for the first I candidates. So what is this value then? It's just 1 over I, right? So plug it in, we're going to have this sum. And that is log n plus some constant. So do you still remember the integral of 1 over x? That's the natural log of x, right? If we try to calculate the definite integral from 1 to n, what do we get? Natural log of n, right? So what is a definite integral? The area under the curve, right? So if you look at the curve of 1 over x between 1 and n, and compare the area, which is log n, and this sum, we can prove that their difference is bounded above by a constant. All right? Therefore, what is the total cost? That will be the expected number of hires, that's log n, times the hiring cost, C sub h, plus the interviewing cost. So see that if the candidates come in random order, it will be much better than the worst case where they arrive in increasing order of their qualities, right? So what do you think? If we always have this random case, never have the worst case, what a beautiful world we will have. That how can we get there? That is the randomized algorithm. So this is the pseudocode of a randomized algorithm. Everything is the same except this line. No matter in which order they come, let's randomize them. All right? And the advantage is obvious. We no longer need to assume that the candidates are presented in random order. In short, there's no bad input. We'll make it good anyway. And the disadvantage is that we must go through this extra step, and it takes time. To randomly permute an array of elements is not a simple task. The main difficulty is to generate a permutation that can guarantee equally likely. So our target is to permute the given array. And here's one solution that works. We just assign each element A of I a random priority, P of I, and sort them according to their priorities. So this is the very simple solution, permute by sorting. Quite straightforward, right? We just randomly generate a number as the priority. Besides this random number, we mod it by n cubed here to make it more likely that all priorities are unique. And that's very important. Okay, after generating the priorities, we just sort A using P as the sort keys. So you see, it's not something difficult to design an algorithm, but it's quite hard to prove that it works. It's been proven that this permute by sorting algorithm produces a uniform random permutation of the input, assuming all priorities are distinct. So see why it's important to make it unique here, right? And this uniform random permutation is what? Say, given n numbers, how many different permutations do we have? N factorial, right? And uniform means that each of the n factorial permutations are equally likely to happen. Okay, so we have seen an offline algorithm for hiring, which means that we have a list of all the candidates in hand, so can make a random permutation before we start the interviews, right? And this method guarantees that we can hire the best person, although it's not so efficient. The expectation of number of hirings is log n. Do you still remember the best case? If they come in decreasing order of their qualities, we only have to hire once, right? What if we just hire once? Then we have to bet on someone being the best, right? So here we go. The point of online hiring algorithm is that we only hire once, and this is the pseudocode. At the very beginning, we assume that in the worst case, we have to interview everyone until the last one. So we initialize the best candidate to be the last one. And the best quality is defined to be something very low, negative infinity. All right? And then we begin to interview the first K candidates. Notice here, besides the candidate information plus the total number of interviews we're supposed to give, there's another parameter passed in, that's the integer K. Okay, so for the first K candidates, we just interview them and obtain their qualities. If their quality is better than the current best quality, update the best quality, but we do not hire any one of them. All right, so after the first K candidates are passed, starting from the next one till the last one, we again interview them. As soon as we find one candidate that is better than, notice here that we have used the first K candidates to set up a quality standard, right? As soon as we find one candidate whose quality is better than the best quality, we update it and break and hire this one. Then obviously you can see that there's no guarantee that the one we hired is really the best one, right? And therefore we have two questions to answer. One is that what is the probability that we hire the best qualified candidate for a given K? Fix any K. What is the probability that we are really hiring the best one? Okay, the second question is, what is the best value of K to maximize the above probability? First, let's try to answer this one. We fix K. What is the probability of this event that we do hire the best candidate? First, we can break this problem into sub-problems. Hiring the best one means that the best one appears after the case one, right? So we can define the event S sub I to be the case when the ith applicant is the best. Then the probability of finally hiring the best one is what? Is the sum of the probabilities of S sub i's for the ones after the case candidate, right? So let's try to get the probability of S sub I first. What needs to happen for S sub I to be true? There are two events that are related to S sub I. So situation A is that the best one is at position I. And situation B is that no one at positions from k plus 1 to I minus 1 are hired. And these two events must both happen so that S sub I can be true, right? And what's important is that these two events are actually independent, and therefore the probability of S sub I is the probability of the intersection of the events A and B, right? And since they are independent, we can break it into the probability of A times the probability of B. So what is the probability of A? That the best one is at some position I. And here we have to again make the assumption that everything happens equally likely, and therefore for every position I, this probability would be what? There are totally n positions, right? So that will be 1 over n. How about the probability of event B? What is the probability that one of them is hired? Again, we would have that equally likely assumption. And therefore, for the first I minus 1 positions, the probability of anyone can be hired is just 1 over I minus 1, right? So this 1 over I minus 1 is the probability that any one of them is hired. And how many candidates do we have between k plus 1 to I minus 1? That will be I minus 1 minus k plus 1, that's minus k minus 1, and plus 1. That is the total number of candidates between k plus 1 and I minus 1, right? So what is this? This can be simplified as this, right? 1 minus k over I minus 1. And this is the probability of B bar, right? That is when B does not happen. So the probability of B would be what? It would be 1 minus this one, which is k over I minus 1, right? So put them together, we have that the probability of S sub I is just k over n times I minus 1. And therefore, we get that the probability of S is the sum of the probabilities of S sub i's, where I goes from k plus 1 to n, right? And to sum them up, since k and n have nothing to do with I, so we can take them out as a common factor. And here again, we see this sum of 1 over I. So the next question is, what is this part? Now I give it as a discussion question to prove that this sum is bounded above and below by these two definite integrals. Okay, try to prove it. Well, I'm sure you can prove it, right? As long as you know what a definite integral is all about. It's just the area under the curve, right? So it's trivial. Now, it's time to answer the first question. What is the probability we hire the best qualified candidate for a given k? And this is bounded above and below by these two functions. Okay, so that's the probability. Next, what is the best value of k to maximize the above probability? We know that the probability is at least given by this function, right? So we can be more specific. Just find the best value of k so that this function obtains its maximum value. So here comes your next discussion question. What is the maximum value of this function, and what is the best k? Well, calculus again. Hope you still remember how to find the extreme value of a function, right? And how to get its critical point. It's the 0 point of its first derivative, right? So go ahead and give it a try. All right. So this is how we obtain the critical value of k. Well, taking k as a variable and differentiate this function. And the first derivative is given by this function, and we set it to be 0 and try to solve this equation for k. And therefore, we obtain that k is simply n over e. We plug this k back to the function. So what is the maximum value of this function? So that means we can succeed in hiring the best qualified applicant with probability at least what? 1 over e, right? E is some constant that is approximately 2.78 something. So this probability is a little bit more than 1/3. So here, an advice to the girls in 非诚勿扰, that is the famous TV match show. The English name is, I guess, If You Are the One, right? And here's the advice from mathematicians. If you know the maximum number of gentlemen you can meet, if you know what that n is, just let go 1/3 of them. Don't pick anyone from the first 1/3. Just use them to set up a standard. And then from the rest of the guys, pick the first one that is above your standard. And the probability of picking the right guy is the maximum, about 1/3.